This video discusses the representation of numbers on a computer. The representation of numbers in a computer involves quite some differences in how we classically write down numbers on paper. Now, different topics will be addressed within this video. Firstly, I'll discuss the difference between decimal and binary representation of numbers. And then we'll talk about the floating point representation and how this allows us to store both very large numbers and very small numbers in a relatively easy and similar fashion. Finally, I'll discuss the standard way of how numbers are then actually converted into bits in computer memory according to a certain engineering standard. So decimal and binary representations. Well, we all know decimal representation because this is the standard way that we deal with numbers in our daily lives. So a number consists of a sequence of digits where these digits consist out of one of a set of 10 possible digits from 0 to 9. And based on the position of this digit with respect to the decimal point, we multiply this with powers of 10. Now an example here is, for instance, the number 60,724.3125. Now we can write this in decimal simply in this way, because this comes very natural to us. This 6, well, let's start at the decimal point to be more precise. So the first digit left of the decimal point gets multiplied with 10 to the power 0, which is 1. So this 4 represents the units. If we move on one further to the left, we will see that this digit 2 is multiplied with the tens. So this 2 represents the number 20. Similar, this 7 will represent 700. This 0 represents the thousands, and this 6 indicates that we have to multiply 6 with 10,000 so that the total number is 60,000 plus 700 plus 20 plus 4. So those are the parts left of the decimal digit. And then to the right of the decimal digit, we have a very similar way, except now the powers of 10 are negative. So the first digit left of the decimal point is multiplied with 10 to the power minus 1. So that's 3 times 0.1. So that's the 1/10. So this is 3/10. Similarly, we have 100ths, 2,000ths, and 5/10,000ths. So if we add all these things together, we come to the number 60,724.3125. And this base 10 number representation comes very natural to us because we also use 10, we also have 10 fingers that we use for our daily computations, and this is probably the reason why we're so accustomed to counting in base 10. Now, an alternative base that we can also represent numbers in is base 2. Now, the big difference here is that instead of digits out of a set of 10, we here have digits that will be selected out of a set of 2 possible digits, so that's either 0 or 1. And each of these digits based on their position with respect to the point is multiplied with powers of 2. For instance, 1 is 2 to the power 0, 2, which is 2 to the power 1, 4, which is 2 to the power 2, 8, 16, etc. And also to the right of the point, we have 2 to the power minus 1, which is 1/2, 1/4, 1/8, etc. Now, these digits in binary, because they can only consist of out of a set of 2, 0 or 1, we can look at them as simple switches, which turn the contribution of a given power of 2 simply off or on. And this is also the reason why this is so amenable to store digits into a computer, because this off or on uh, behavior of the binary representation translates very well to having switches on a computer board set to 0 or 1. So some examples for simple numbers, or the first 4 numbers in base 10 in base 2. So let's take a look at the number 1 in base 10. So that is 1. We can simply write this as 1 in base 2. So this is 1 times 2 to the power 0 plus 0 times 2 plus 0 times 4 plus 0 times 8. So we can simply retain the rightmost binary digit and get rid of the leading zeros. So a 1 in base 2 is the same as a 1 in base 10. How do we represent the number 2 in base 2? Well, similarly, we take a look at which switches, which contributions of these powers of 2 have to be switched on in order to form the base 10 number 2. Now that's very easy because there's only one contribution that we have to add, and that is the contribution of this 2 to the power 1. So the representation of the decimal number 2 in binary is 1, 0. And we can get, again, rid of these leading zeros, but we can also simply leave them there. So 0, 0, 1, 0 is the number 2 in base 10. Similarly, we can go to 3, but then we have to switch on the contribution of 2 to the power 1 and 2 to the power 0, because then we get 1 plus 2 is 3. And for 4, we simply have to switch on the contribution of this power 2 of 2. So that's quite straightforward. For these low numbers, it's very easy to convert them to binary. Now, let's take a look at a slightly more complicated decimal number, 19.625, and try to convert this into a binary format. Now, what I always do when I have to convert numbers into a binary format is take a look at kind of a cheat sheet and place that on top of the paper where I have to write stuff down. And this cheat sheet, well, it basically gives me the powers of 2 in base 10 representation, which allows me to easily turn on and off the switches that are needed to form the decimal number that we have to convert into binary. So let's give this a try. So the number 19.625, it consists of both the whole part to the left of this decimal point and the fractional part to the right of the decimal point. And let's treat them separately, as this is a bit easier to explain. So let's start with the part to the left of the decimal point, 19. So we have to form 19 out of powers of 2. Now, how will we do this? Well, we start, for instance, from 2 to the power 5. This could also be 2 to the power 6 or 7, but we will clearly see why we don't go to higher powers in a second. And we try to fit this contribution, so this 2 to the power x, into the number that we want to form. And if it fits in there, then that's good. And we put a 1 and we subtract that to get a remainder. If it does not, we simply put a 0 and we still have to form the remaining 19. So let's take a look here. So we start with 19 and check whether 2 to the power 5, which is 32, fits into 19. Well, that's not the case. So we put a 0 there, and uh, the remaining number that we still have to fill in is still 19 because we could not put a 1 here. So it's still 0. We still have to form 19 out of the remaining powers of 2. Let's see whether 16 fits into 19. Well, yes, that's the case. So this means we can put a 1 there. So we already have then 16 formed. So we can simply subtract this from the remaining 19, which means that we still have to take care of 3 units that have to be formed using powers of 2. So moving on, we can take a look whether 8 fits into 3, and that's not the case. So we put a 0, and this remainder is still the same. Similar for the power of 2, which is 2 to the power 2. So 4 also does not fit into 3. So again, a 0, and we have this remaining 3 still there. Now things become a bit easier. So we know that the number 2 fits into 3. So we put a 1, subtract 2, and have as a remainder 1. And then finally 2 to the power 0, which is 1, fits into 1. And we have here as a remainder simply 0. So this means actually that the number 19, so the number 19 in a binary format can be read as 10011. And I just skipped this leading 0 over here. Now for the fractional part, so the 0.625, we just do a very similar approach. So I write it over here. And now I take a look at the negative powers of 2. So 1/2, 1/4, 1/8, etc. And try to form again this 0.625. So let's start. Firstly, does 0.5 fit into 0.625? Well, yes, that's the case. So we put a 1 over here, we subtract 0.5 from 0.625, and the remainder is 0.125. We try to fit 1/4 into the remainder, and that doesn't work. So this will be a 0, and this remainder remains unchanged. And then we see here clearly that this 1/8 is exactly fitting into the remainder, so we can put a 1. We don't have to deal with any remainder anymore, and we are finished. So 0.625 in binary would be 0 point, because we are to the right side of this point over here. So this would be 0.101. Adding these two together, well, we can say that 19.625 in decimal is simply 10011.101 in binary. Now in the notation in these slides, to avoid any confusion, I will always add this subscript B when I'm talking about binary representations of numbers instead of decimal representations of numbers. Let's look at a different example. And in this second example, let's take a look at the number 41.34375. And I would highly encourage you to pause the video and try to find the decimal representation of this number by yourself, and then check it after you've found the result by resuming the video. And I will give you a second to pause the video if you want that. So the approach to convert this decimal number into a binary format is completely analogous to what we've been doing in the previous slide. So we start with the wholes. So we start with the stuff on the left side of the decimal point. So for 41, we try to fit in 32. Well, that gives us a 1. 41 minus 32 gives us as a remainder 9. 16 does not fit into 9, so that's a 0. 8 fits once into 9, so that's a 1. And we have as a remainder 1. And now we can already actually see that 4 and 2 will not fit in there, and this one will. So we see that the final binary representation of the number 41 is 101001. Similarly, for this fraction to the right of the decimal separator, 0.34375, well, 0.5 does not fit in there. 0.25 does, so we put a 1, we subtract, and we get this remaining 0.09375. 0.125 does not fit into this remainder, so we have a 0. The 0.0625 fits in there once, so we have this remainder, and we see that that's exactly equal to 1 over 2 to the power 5. So we get a 1, a remainder of 0, and we have our final decimal representation of this number, which is reading from left to right 101,001,01011 in binary. So far, so good. Now let's take a look at a slightly more interesting or complicated case. The simple or relatively simple number in decimal, 0.1 or 1 over 10, 1/10, and try to convert this into a binary format. And again, I would encourage you to try to do this by pausing the video and seeing whether you can find the binary representation of 0.1. If we try to convert 0.1 into binary, well, we see that here we have a 0 because 1 does not fit into 0.1, neither does 0.5, neither does 0.25, neither does this one, but 0.0625 does. In this remainder, 0.03125 also does. Again, we have in this remainder, neither this nor this will fit. We have again 2 zeros. As this gets smaller, well, will start fitting again. So this will give us a 1. This is also smaller than this, will give us a 1. This is larger than this, will give us a 0. So we see that this will have a lot of binary digits. It seems to be hard to find actually fitting numbers to nicely represent 0.1 in binary. And actually, it's the case that, well, you can keep on doing this forever. So you can keep on adding digits or bits to your binary representation, but you will never exactly fill the decimal number 0.1 into a binary format. You will get closer and closer and closer. We see that this remainder gets smaller and smaller, but with a finite amount of powers of 2, you can never form 0.1. So just as a short recap, we looked at these 3 decimal numbers and converted them into a simple binary format in the previous exercises. We will revisit these numbers in a few slides again. Also, an important term that I would like to introduce here is the specific term for a binary digit, which is a bit. So binary digit is a bit. And several decimal numbers can possibly be represented using a different amount of bits. So here we see that 19.625, which can be represented in decimal with 5 digits, requires 1, 2, 3, 4, 5, 6, 7, 8 bits in binary. The simple decimal number 0.1 cannot be represented using a finite amount of bits. For reference, actually, a number which cannot be represented using a finite amount of decimal digits is, for instance, the number 1 divided by 3. That would be 0.333333, and then infinite amount of decimal digits behind, following behind that 0.333. So there are certain numbers that you simply cannot represent in a certain base using a finite amount of digits or bits in binary. Let's take a look at some scientific numbers, and then it becomes clear that we have various scales that we need to address in computational science. For instance, let's say that we want to do computations which involve both the elementary charge of an electron or a proton and Avogadro's constant, which indicates how many particles or molecules or atoms there are per mole. And we see that we have both very large numbers and very small numbers. And these numbers are hard to represent. Let's say with a standard decimal notation, well, here this requires already quite amount of decimal numbers, but in binary it gets even much worse. So this is a very long string, and it's even truncated here at the end, of bits required to represent this very small number. Whereas Avogadro's constant, that has about 23 zeros here, so that's a very big number in decimal representation, but also in binary representation, this requires a very large amount of bits in order to represent this number in binary. Now, it's important to note that we would need to do computations with numbers of all possible scales. We want to have the freedom to do this in our numerical simulations. So we want to both store very small numbers and very large numbers efficiently. However, the current representation, as on this slide, would mean that in order to store all these relevant scales in the standard representation, this would require a huge amount of bits or a very large amount of computer memory in the end. So something else has to be used here. And this something else is the floating point representation. Now, in floating point representation, well, we basically rewrite the number into this form where this has three main parts. So we have a leading non-zero digit, which is then placed before this point, which floats. We have the part of the number which comes after this point, which is called the mantissa. And then we multiply this with our base times an exponent. Let's try to make this a bit more concrete by looking into a very specific base, and that is base 10. And for base 10, floating point representation is simply known as scientific notation. And that's something that most of you will probably already have seen somewhere through their curriculum. So in scientific notation, well, this leading digit before this leading non-zero digit can be from 1 to 9. We can have a mantissa, which possibly has can be a very long mantissa, which also has in every position a number from 0 to 9. Note that this cannot be 0 because it's the leading non-zero digit. So here we have all numbers from 0 to 9, and then we have times 10 to a certain power, and this is an integer power in base 10. So looking at some examples, for instance, this number over here, 0.000, etc. This can be more compactly written in this form as 1.602176. So we have this 1, which is a leading non-zero digit. We have here a mantissa of 6 digits. We have base 10, and the exponent is minus 19, because in order to move this point up until here, we would have to move it 19 places to the left. Similarly, for very large numbers, this is Avogadro's constant. This can be much more compactly written as this, where we have as a leading non-zero digit 6. Then we have our floating point, a mantissa of 0 to 2141 times 10 to the power 23. And this 10 to the power 23 is because from moving from here to here, we would have to move the point, which in this case is located on the right of the last zero. We would have to move that point 23 places. So that is base 10 floating point, which is something that is comes quite natural to most people, at least studying science and engineering. Moving on to base 2 floating point, well, not that much changes. The leading non-zero digit, well, this will always be a 1 in this case. So for a base 10 floating point, well, this could be 1, 2, 3, 4, 5, 6, 7, 8, or 9. In base 2, well, we only have two possible values for our bits, either 0 or 1, and if the leading digit is non-zero, then this is a 1. So this 1 in front of the floating point is implied, and that also means that we don't have to store it, and that will come in later as a handy thing. Here we have then the mantissa, which is also simply a long list of binary digits or bits which can attain numbers from 0 or 1, and also the exponent is written in binary representation. Let's now look at some examples for base 2 floating point, just like we did for base 10 floating point numbers. Okay, so let's now convert some decimal numbers to binary floating point numbers. So we will look into the same numbers that we used before, where before we just simply converted decimal numbers into binary numbers. Now we will further convert them into binary floating point representations. Okay, so let's take a look at this binary number. First, we have to identify what the mantissa would be. Now the mantissa is the part on the right of the leading non-zero digit of the binary number. Looking at this binary number, well, the leading non-zero digit is simply this one over here, and it would always be the first one that you encounter when reading from left to right. And since we don't add the leading zeros in standard representation, this is simply the first number, always the first one that you encounter. So the mantissa in this case will be all the numbers to the right of this one. So the mantissa will be 0, 0, 1, 1, 1, 0, 1. And that is this mantissa over here. Now we have to identify the exponent. Well, the exponent is the power of 2 that we have to multiply our floating point representation with to get the original binary representation. And this in this representation, you can easily read this off by checking how many places we have to move this point, the floating point, to move it right next to this leading non-zero digit. And this is, in this case, this is 1, 2, 3, 4 to the left. So this means that we have to multiply with 2 to the power 4 to go from this representation into this one. So we have an exponent of 4. However, note also that in binary floating point representation, we need to make sure that our exponent is also written in base 2, so in binary. So let's pop up our cheat sheet over here and let's take a look at what the number 4 in binary would be, while going from right to left. So this would be 0, 0, 1. that would be 4 in binary. So in summary, converting 19.625 into binary floating point, well, we already saw how to convert it to standard binary representation. We saw how the mantissa can be split out. We saw how to convert this exponent of 4 into the binary notation 100. Well, then writing this in binary floating point is just the leading non-zero bit, which is always 1 in binary floating point. We have here the mantissa 001101 times 2 to the power 100, which is the number 4 in binary representation. So now looking at our second example, 41.34375, which we already readily converted into binary format 101.001.01011. Let's convert it now to binary floating point. And again, you can pause the video if you want to do this by yourself first in order to get some exercise. And I will give you the chance to do that. So the mantissa is everything to the right of this leading one. So this will be 01001011011. And so that's simply equal to this over here. We have to check for the exponent. So how many positions do we have to move this floating point to attain a form in this standard floating point representation? So this means we have to move this digit with 1, 2, 3, 4, 5 places to the left. So the exponent will be 5. Looking at our cheat sheet, how do we make 5 out in binary representation? Well, 5 is 4 plus 1. So in binary, this will be 1, 0, 1. So 5 in binary is 101. And then combining all these things together, we can find that the binary floating point representation of the decimal number 41.34375 is simply equal to this, where this is the mantissa and this is the exponent. Again, we can also look at how this looks for the decimal number 0.1, where we saw that the binary representation holds an infinite amount of bits. Also, the mantissa in full precision would hold an infinite amount of bits. In this case, well, the exponent, so the leading non-zero digit here is this 1. So this means that the mantissa starts from here. So we have to check how many spots we have to move this floating point, to go to here. And this is 1, 2, 3, 4 spots to the right. So this means that the exponent in floating point representation would be -4. Again, 4 in binary is 100, so -4 translates to -100. So in binary floating point representation, 0.1 would be simply this 1.100, 1100, 1100, 1100, etc. times 2 to the power -100. So this is all once you've gotten the idea of how to convert decimal numbers to binary numbers to binary floating point numbers. This is not very, very complicated. So once we have the floating point numbers in standardized binary floating point representation, we need a convention or a standard as to how we actually store this mathematical, so it's still a mathematical representation of this number, into computer memory. So we have to convert this to a string of zeros and ones. So we have to, for instance, get rid of the sign. we have to get conventions on how to store the mantissa and how to store the exponent as well into this string of computer memory. So for that, the IEEE 754 standard was invented, and it's already from 1985, but it's by far the most prevalent way with how floating point numbers are stored in computers nowadays. Up until now, all that we've discussed is actually pure exact mathematics, whereas this IEEE standard it's more computer science. So here we move on from the pure mathematics that we discussed so far into a standard defined by engineers as to how to store these numbers in a computer. Now there are two main standards within this IEEE standard. There are two main types of floating point numbers and how they're stored, and those are what's called single precision and double precision. And within single precision, we use a total of 32 bits in computer memory to store our floating point binary number. With double precision, we use 64 bits. And in different programming languages, they all support these different types of precision for floating point numbers, and you can find them in various names. For instance, the C language uses float or single for single precision. Fortran uses real, kind is 4, etc. So if you encounter any of these names when programming or when reading scientific programs, you can assume that it is a single precision or a double precision floating point number that you're encountering here. So let's take a look at how this is actually done in practice then. So this binary floating point representation has to be converted to a large string of bits. Now, single precision uses 32 bits, double precision uses 64 bits, and you see here in this table how many bits are used for which part of this floating point number. So the sign, well, for the sign, we always just use one bit. So the sign can be a plus or a minus. Now, if the number is positive, we store a 0 for the sign. If the number is negative, on the other hand, we store a 1. Moving on to the exponent. Well, for the exponent, single precision uses 8 bits. Double precision uses 11. The exponent is stored in a somewhat peculiar way. So instead of simply storing the binary form of the exponent straight into this register of 8 or 12 bits in computer memory, we first add a bias to this exponent. Now, why do we do this? Well, this is simply to avoid negative numbers when you store the exponent. Now, for the rest of the examples here, we will be talking about double precision numbers, so we can kind of neglect the single precision, because double precision is what's mainly being used nowadays in scientific computing. And in double precision, well, we add a bias of 1023, such that all possible exponents that we can store kind of correspond to a positive number. Let's take a look at what this means. Let's say that our real exponent is 0. So we have a 2 to the power 0 here in the base and the exponent. Well, then we have to add to this 0 the number 1023. So that's the bias. So the exponent plus bias that we have to store is 1023. And in binary, this would be 0, 1, 1, 1, 1, 1, 1, 1, etc. If we want to store a negative exponent, well, then we have to add again this bias. So minus 5 plus the bias, well, that's still a positive number, 1018, which translates to 0, 1, 1, 1, etc., 0, 1, 0 in binary. So even though the original exponent is negative, the exponent plus the bias is a positive number. And in that case, we would simply store this string of 11 bits into the registers available for storing the exponent in double precision here. For a positive exponent of 5, well, we would add 5 plus the bias of 1023, which is 1028, which would be this string that would be stored into the exponent. So that's kind of a trick that's being used. So there is a bias to be added to the actual exponent in order to avoid having to store again an additional bit here for the sign of the exponent. So we only store positive numbers here for the exponent plus bias. Now this will become more clear when we look at some examples in the next slides. The mantissa then finally is relatively straightforward. We simply store the mantissa in binary. So in double precision, we have 52 bits available for storing this mantissa, ranging from the contribution of 1/2 2 to the power minus 1 to the contribution of a very small number 2 to the power minus 52. So we have quite some space here for the mantissa in double precision. Let's take a look at storing one of our examples here, 19.625 in a double precision IEEE floating point representation. Now in previous slides, we looked into converting this into binary, separating out the mantissa, taking a look at what the exponent would be and converting it to binary floating point. Now we will investigate how this number 19.625 is actually stored into computer memory according to the IEEE 754 floating point standard. Okay, so let's start with the first bit for the sign. And recall that for the sign, we store a 0 if the number is positive, and we store a 1 if the number is negative. 19.625 is positive, so we simply store a 0 here. For the exponent, well, the exponent here is 4. Because of this stuff with the bias, well, we have to add first a bias, which is 1023 in double precision. So the actual number that we store in the registers available for the exponent and bias is 1027, which when converted into binary is 1000000011. So we just plug that into there, and the computer knows that when we store this, this means that the exponent plus bias is 1027, so the actual exponent would be 4, because we have taken account of this bias over here. Now the mantissa, which is 001101, that can simply be stored directly in binary representation. So this 0 is the contribution that gets added to the 2 to the power minus 1. So that's what comes to the right of this floating point. So we simply fill that in from left to right and add trailing zeros for the smaller and smaller contributions, which are 0 in this case. So the mantissa here is 001111, 0, 1, and then we just fill this up with remaining zeros because there are no contributions from smaller powers of 2 in our mantissa. So in summary here, we have that 19.625 converted into IEEE 754 floating point double precision representation is 0, 1, blah, 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 1, 1, 0, 0, 1, 1, 1, 0, 1, and then a large string of zeros. So when we think of 19.625, the computer thinks it's actually this number, or sees it as that number. Now, again, let's take a look at our second example. Again, like in the previous cases, take a look whether you can figure this one out yourself before you continue the video. So you can pause the video now if you would like to do that. Okay, so first off, the sign, well, we know it's 0 if the number is positive, it's 1 if the number is negative, so we just add a 0 here. For the exponent, well, the exponent is 5. We add the bias 1023, so that becomes 1028, which converted to binary is this. So this is the exponent plus bias as stored in memory. And then finally the mantissa, we have 0, 1, 0, 0, 1, 0, 1, 0, 1, 1. We store that and add a large number of trailing zeros in this case because the mantissa here is finite and only has a quite limited amount of digits. So we don't actually need all these zeros, but we need to store it anyway because of the IEEE standard. Now looking at our problematic case of 0.1, well, if we then again perform the same exercise, we look at the sign, which is 0, the exponent, which was -4, which translates to 1019 after adding the bias. So we store this binary number as the exponent. But the mantissa is where we start running into trouble. So this mantissa is never ending. It is 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and that keeps moving on to infinity. However, we only have 52 bits available for storing the mantissa. So if we try to do this, well, this is exactly 52 bits. Well, then we can only go up to this one over here, and we cannot store this one or any of the trailing zeros and ones that come after it. So we have to somehow get rid of all these trailing numbers after this one. Now, what actually is the standard way of doing this? Well, is that we round this. So actually this one and this one is rounded to a decimal, to a binary representation of 1, 0. So because we had a 1 here first and we had a 1 which was truncated, rounding that up causes this mantissa to be converted to this over here. Now, this is a important statement to make. If we were to convert this IEEE representation, this IEEE floating point number back into a decimal number, this is not exactly 0.1. 0.1 cannot exactly be represented in a floating point representation with a finite amount of bits. So your computer actually has no idea of, or has no notion of the exact number 0.1. It will always see this as 0.10000, etc., 555. So this is why sometimes your computer will tend to give rounding errors, for instance, because 0.1 is not in the library of possible numbers of your computer, and instead it rounds it to the nearest floating point representable number, which is 0.1, 000, etc., 555, 11, etc. So this is important to keep in the back of your mind, that not all real numbers can be represented in floating point numbers with a finite amount of bits. So there is a lot of rounding going on whenever you convert a real number which does not have a finite representation in binary to a IEEE floating point number. Some additional notes on the IEEE standard. There are some special numbers which have a dedicated representation. For instance, plus or minus infinity. For those numbers, the addresses where the exponent is all equal to 1, so that would be the maximum allowable exponent. The mantissa is equal to 0. Then we get plus or minus infinity, whether this is a 0 or a 1. If it's a 0, it's plus infinity. If it's a 1, then the computer reads this as this number, not as a very large number, but as minus infinity. Similarly, if the exponent is all ones, so that's the largest number that it could possibly represent using this exponent, but the mantissa is non-zero, well then this is not a number. Well, not a number is basically what you would get if you perform a illegal operation, taking the logarithm of a negative number, for instance. Also, the number 0 is represented in here. If we were to convert this into using our standard rules into a decimal number, this would yield a very small but non-zero number, because this exponent would be translated to minus 1023, 2 to the power minus 1023, which is very small but not equal to 0. But the standard actually tells us to convert this. Well, we just say that it is equal to 0. Now, what would be the smallest number and the largest number that is possible to be stored using this IEEE representation? Well, for the smallest number, well, we would take the smallest exponent, which is not reserved for this actual identical 0 element. So the smallest exponent, which is non-zero, would be 0, 0, 0, etc., 1. With a mantissa of zeros, well, converting this to binary floating point, this would be 1 point and then an infinite amount of zeros in binary, times 2 with an exponent of 1 minus the bias is minus 1022. And if you compute this, well, this would be the smallest possible non-zero number that a computer can store. So note that this is very small, but for instance, a number 1 times 10 to the power minus 309 could not be stored as a floating point number in the IEEE standard. So this means that there is a gap between 0 and this smallest possible number. And whenever you have actually a result of a computation that would fall in this gap, that's when we talk about the phenomenon of underflow. So that would mean that the result that you actually get is smaller than the smallest possible number representable by a computer in floating point notation. Similarly, we can take a look at the largest number. So for the largest number, we take the largest admissible exponent, which does not correspond to one of these special numbers for infinity or for this none, not a number. And that would be 1, 1, 1, 1, etc. And then with 1 trailing 0. And to that we add simply a full mantissa of 53 bits with all ones. So this would be 1.11111, etc. 1 times 2. Now this number converted into decimal is 2046. Subtracting the bias gives us this number. So this would be 1.11111 times 2 to the power 1023. Now this is very close to simply 2 to the power 1024, which is approximately 1.8 times 10 to the power 308. So this is the largest number, whether positive or negative, that can be represented using this floating point notation in double precision. If you have a number which would happen to be larger than this largest number, then that is something that the computer cannot cope with in IEEE standards, and that is what is called overflow. I now want to discuss one of the, let's say, peculiarities of storing numbers in this IEEE standard. And that is that there is a finite distance between two consecutive IEEE floating point numbers. So we already discussed what is underflow and what is overflow, so numbers that are too small or too big to be represented in IEEE 754 format. However, the range of numbers that can be represented still holds a finite amount of floating point numbers. Not all possible real numbers, so there are an infinite amount of real numbers within the range of numbers that can be represented, but not all these real numbers can be actually represented into IEEE 754 format. So there is a finite and non-zero distance between each and every IEEE floating point number. And let's take a look at the number 1 in IEEE floating point. So let's call this number A. And how do we denote this number? Well, 1 is equal to 1 times 2 to the power 0 with a mantissa of 0. So this means that, well, the exponent is 0, so exponent plus bias is 1023. So in this register where we store the value for the exponent plus bias, this is 1023 in binary, so that's 0, 1, 1, 1, 1, 1, etc. And as a mantissa, we have zeros. Now, what would be the adjacent IEEE floating point number, which is larger than 1? Well, the sign would simply be 0 again. The exponent would be the same, but in the mantissa, we just add the smallest possible difference between A and B. So we just add a 1 in the very last digit of the mantissa. Okay, so converting this into a binary number is not hard. So this is 1.000, etc. And then at the 52nd place after the decimal point here, not the decimal point, after this point here, a 1 would occur. So we have this would be this number in binary. Now we can compute this difference. So that is simply 0 points, and then we have 51 zeros and then a 1 in binary. So this is 2 to the power minus 52, or roughly 2 to the power 10, 2 times 10 to the power minus 16. So that is the difference between the number 1 in floating point representation and the floating point number right next to it. In between A and B, there are no possible floating point numbers in IEEE representation in a computer. So everything that is in between A and B will get rounded either to A or to B. So that is again an example of a rounding error. Now this is a very specific distance, this distance between 1 and the closest floating point number next to 1, and that is what we call the machine precision. And in MATLAB, you can check what this machine precision is by simply typing EPS for epsilon, and that will give you this number over here, 2.22 times 10 to the power minus 16. Now, the distance between two floating point numbers is not the same across the range of all representable numbers. So in the previous slides, I told you that if the distance between 1 and the next adjacent floating point number is 2.2 times 10 to the power minus 16, which is the machine precision. Now let's take a look at this distance between two floating point numbers for numbers which are much larger. So for instance, let's take a look at numbers where we have an exponent of 45 instead of an exponent of 0. So we have an exponent of 45. Well, this would translate to this for the exponent plus bias. And to make the smallest observable difference between two floating point numbers, well, we just add a 1 to the very last digit of the mantissa. So number A is actually equal to 1 times 2 to the power of 45, and the number B would be 1.00 and then a lot of zeros, so this is 52 zeros and then a 1 in binary representation times 2 to the power of 45. Now what would be the difference between these two adjacent floating point numbers? Well, we can see that this is actually a lot larger. So for these very large numbers, well, a minus b is simply equal to this mantissa, so 0.00, so this is 51 zeros and then a 1, times 2 to the power 45. So we have that this is actually equal to 2 times 2 to the power minus 52 plus 45, which is 0.008 approximately. So that means that between numbers a and b, they are very, very large, but the distance between them, well, it's not negligible. So in a range of 0.008, there is a gap where there are no floating point numbers available within this IEEE double precision standard. So everything within this gap would be rounded either to A or to B. Now this wraps up what I wanted to say about the representation of numbers on a computer. I introduced the concept of decimal versus binary representations, base 10 versus base 2, and how base 2 is quite amenable to computers because it has this switch on, switch off behavior for every bit. We discussed how floating point representation is kind of a solution as to store both very small and very large numbers in an efficient way. Finally, we discussed how to store a number into computer memory. And for this, we use the IEEE 754 standard, which is the worldwide standard today. And one of the key points I want to make, or I wanted to make throughout this video, is that not all numbers can be exactly represented within this standard. So there is rounding error. Some numbers simply do not have a finite binary representation, like the number 0.1. Some numbers are too small, which is when you have underflow. Some are too large, which is when you have overflow. And it's also quite possible that your number, your exact number, is not exactly representable in this floating point format, and that leads to rounding errors. And in the next video, we will talk a bit more about errors and their impact on the solution in numerical methods.